Welcome. I'm Barbara Giunti, a postdoc at the TU Graz, and today I'm going to talk about the clear and compressed optimization for the persistent algorithm. So for following this tutorial, at best, it is nice if you know what is a boundary matrix. But do not worry, even if you're not familiar with the concept, you will be able to follow. Also, for getting a geometrical interpretation of what we are going to do today, I strongly suggest you to take a look at the video of Teresa Heiss, which is again in this series of tutorial. Okay. Finally, the motivation for this tutorial is to compute the barcode. So I hope you're already convinced that it is really useful for that analysis. Let's get started. Okay, so given a matrix, any matrix, we can define the column pivot of a column of it in this way. So we take a column J and we look at its lowest non-zero element. And then we look what is the row index of such element, and that is going to be the pivot of that column. We denote it by I equal low of J. Given a matrix, then we can use this pivot, and this is true for any matrix, even if we are just considering boundary matrix. We'll consider this matrix to be reduced if any two non-zero column J and J prime have different pivots, which means their lowest element are in different rows. So let's look at an example. For example, this matrix here is not reduced because I can take this column and this column, and you can see that the lowest element in both of them have the same pivot, which means it is in the same, the lowest element is in the same row. But if you take a look at this other matrix, then you can check and you will see that this is actually reduced. So why do we care about reduced boundary matrices? Well, because if we have a boundary matrix, then these pivots that we get by left to right column operation are uniquely defined. And also, every time we have a pairing of pivot, which means that I have I, which is the row index of a column J, then I have the interval ij in the barcode decomposition. And this is known as the pairing lemma, and at the best of my knowledge, the first presentation of it in this shape is due to Cohen-Steiner, Edelsbrunner and J. Okay, so let's look at an example. Let's take a filter simplicial complex, and if you do not know what is it, do not worry. It's just a nested sequence of simplicial complexes, which means that at the passing of one parameter, we have, at the beginning, we have, for example, just the vertices, and then we add also edges and the face of this triangle. And this can go on in a higher dimension also. Okay, so given a filter simplicial complex, we can get its boundary matrix. Now, this is actually boundary matrices because here, this is D0, so the boundary matrix in degree 0, here is in D1, and here it is in degree 2. Okay, now, in this case, I'm on zeta 2, which means that these dark squares are 1s for me. And also, every time I add two of them, I get 0. So now let's take a look on how to reduce the boundary matrix. Well, we do it with column operation from left to right, which means that we take a column and we take its pivot, and if it's unique, then we go on. We take the second one, and its pivot is already, we had it already. So we add the two columns together, and we keep doing it until we find a pivot that it was not there before, or the column is 0. So for example, in this case, you can see the pivot is unique, and so we go on. But in this case, we already have a previous column with the same pivot, and we add them. And then we keep doing it until the column, well, in this case, is 0. Okay, and now what we have at the end is that we have this pairing. Okay, namely, we have this matrix. Now, as I said, for the geometrical interpretation of it, check the video of Teresa. But what is important basically is that this pivot, for example, between which is in row sigma 5 and in column sigma 6, is telling me that I have an interval 5, 6 in the barcode decomposition. Now, when we compute the barcode, we usually want to have, or we hope to compute it for very big matrices. So we would like to be as efficient as possible. How can we do it better? Well, we didn't use the property of a boundary matrix, which means that a boundary map, which is that when we apply it twice, it gets to 0. So how it is translated for us? Well, it means that if at the end of the reduction, I know that a simplex has an image, okay, then it means that it cannot have a pre-image because otherwise the composition will not be 0. So what does it mean? It means that if it is the ending point of an interval, okay, if it is the ending point of an interval, it cannot be the starting point of another interval. At the same time, if a simplex has a pre-image, then it means that this image is 0. So this means that if it is the starting point of an interval, it means that it cannot be the ending point of a previous interval. So what it means for us is that every time I found a pairing, so I found a row I such that which is the pivot of a column J, then I know that there does not exist another column J prime such that J is the lowest element in that column. So what it means is that we can put the row J to 0, and this is what we call it the compress. Okay. At the same time, if we have this pairing, so I is equal to J, then we also know that the column I, it will be 0 at the end. It cannot contain any pivot. And this means that we can put it to 0 immediately and call it the clear. Okay. So let's try to apply this to optimization. Well, we run into some problem, namely the fact that the compress decreases the number of rows, but we are going by columns, and the clear set to 0 a column that we already reduced it because we go left to right, and I is comes before J. So how do we solve these problems? Well, first, we can reduce by row, or we can try to see if it's possible to reduce by row. And second, we can start from the top degree. So instead of going from D0 as we did before, we go from D2. So let's start and take a look at what happened there. So when I apply the clear optimization to the column reduction. Well, what is happened is that I start with the last, and then when I found a pivot pairing, then I know the sigma 5 cannot contain any pivot, and I can put it to 0. And I keep doing it. So here I have the pair sigma 2 and sigma 4. Then sigma 2 cannot contain any pivot, and I set it to 0. And at the end, with much less of operation, what I found is the same pairing as before. So we can do this. And now let's take a look at this one. Well, to reducing by row, we do basically the dual of what we did so far. So instead of considering a column, we consider a row. So given a row, we take its leftmost element. So given a row I, we take its leftmost element, and we take the index of that element, which is going to be, in this case, J, and we say that this index is the pivot of the row I, and we write it like this. J is the leftmost of row I. Okay, and we can give the definition of what it means to be a row reducer by saying that in a matrix, or in a boundary matrix specifically, every two non-zero row I and I prime needs to have different pivot, which means that their leftmost element has to be in two different columns. Okay, so let's take a look at an example. In this case here, the matrix is not reduced because I can take, for example, this row and this row, and you can see that the leftmost element here and the leftmost element here, they share the same pivot. They are in the same column. But if you take some time and check this matrix here, you should see that it is reduced. Okay, now we can prove very easily, actually, the equivalent of the pairing lemma also for when we go by row. So namely, we have that the row pivot are uniquely defined when we compute them by bottom to top row operation. And also if we find a pairing, so if we find that J is the leftmost element in row I, then what we have is that we get the interval ij in the Barkov decomposition. Okay. So if we check again with our example as before, the filtered simplicial complex, we take its boundary matrix, and now what we do is we apply. But remember, this time we follow the matrices, but we need to start with the lowest row in every matrix. Well, for this 0 doesn't change so much. We have just one. We take the leftmost element and we go on. Here we start from sigma 2. And then we check if the leftmost element, if any previous row has a leftmost element in the same column, like in this case. And then we add them, okay, until they are either 0 or we find a unique pairing. So this is what happening also here. We take the leftmost element and we notice that we already have a row with the same pivot, and so we add them and go on. Now, at the end, what we get is that we get, again, a pivot pairing. And if we take a look, okay, if we take a look, this is the row reduced, okay, and this is the column reduced. Okay, now you can see that the matrices are different. For example, here I have a non-zero element, which is not here, and here I have 0. And here I have a non-zero element. But the pairing, so the red squares, they are the same. Okay, so the pivot pairing is still there. Now, the reason why we wanted to go by row was to apply the compress. So let's take a look at what had happened here. Well, what it happened is that now we find that sigma 0 is part of a pairing, so we can put this row to 0. Because we know we will not use it anymore. And the same things for sigma 2 and sigma 4. So sigma 4, it will be put to 0, and sigma 3 also in here. So at the end, we end up with doing less operation, so less addition, but with the same pivot pairing. So if you wonder what is best, so to apply the clear optimization going top down in degree, and using column operation, or apply directly, so bottom up in degree, the compress optimization using row operation, well, the answer is it depends on your data. But just keep in mind that these operations are one the dual of the other, and so you can freely pick what is best for your application, so what gives you the barcode in the more efficient way. Okay, that was everything I wanted to tell you today, and I hope you enjoyed. Goodbye.